Welcome to part 5 of Module 201B. This video is going to be on a brand new concept to you concerning AC circuits and AC circuits alone. The concepts that we're going to talk about do exist in DC circuits, but only for a fraction of a second, so therefore they're not really relevant to our conversation. What we're going to talk about is impedance. In first year, we taught you about resistance, which is the direct opposition to current. However, with an AC circuit, there's two other types of opposition to current that you need to be aware of, and we're going to cover these in greater detail as we go on through the course. But those other two types are inductive reactance and capacitive reactance, and they both oppose current in their own individual ways. Now, if we take inductive reactance, capacitive reactance, and resistance, the culmination of all these three different components together gives us what's called impedance. And normally, in first year, when we talked about the resistance of a circuit, that's all we really had to concern ourselves with. However, now that we're dealing with AC circuits, instead of dealing with resistance, which is only one part of the piece of the puzzle, now we have to deal with impedance, which is the full picture of all different types of opposition that we could have to our current. Let's do a review on resistance. A resistance is an opposition to the flow of electrons, and the higher the resistance is, the less the current that we have. That does not change whether we have an AC or a DC circuit. Resistance will always be the physical opposition to current flow. Another property that could be found in our circuits is called inductance, and we have inductance anytime that we have a coil. That coil could be found inside a motor or a transformer or in a fluorescent or LED lighting. Any type of coil will have the property of inductance. An inductance is when the magnetic field of one wrap of the coil affects the voltage of another wrap by producing what's called a counter EMF. And we'll get into that a bit more in detail later. What you need to understand is that the inductance is a property of a circuit that opposes any change in current, and it creates what's called inductive reactance. A third property our circuits can have is what's called capacitance. A capacitance is whenever we have a capacitor inside the circuit that will hold a charge. In a DC circuit, that charge would be held and it would stay held until it was discharged. However, in an AC circuit, that charge is constantly building and discharging and building and discharging. A capacitor's job in an AC circuit is to oppose a change in voltage. So capacitance is the opposition to a change in voltage. And since voltage and current are directly related, if I oppose voltage, I also inherently oppose current. Capacitance will create what is called capacitive reactance, which is the third part of our puzzle. When we talk about impedance, we need to think impedance as the total opposition to current. So if I take into account all the different parts of my circuit, whether it's resistance, inductance, or capacitance, the total opposition of all those different compounds gives me what's called impedance. And impedance is a total current limiting process of an AC circuit. Resistance has a direct opposition to current. Inductive reactance has an opposition to the change in current. Capacitive reactance has an opposition to the change in voltage, which subsequently also opposes a change in current. When we look at the three different parts of impedance, every part of this is measured in ohms. Our resistance is measured in ohms. Our inductive reactance is measured in ohms and represented by the letters XL. Our capacitive reactance is measured in ohms and represented by the letters XC. And our total impedance is measured in ohms and is represented by the letter Z. Normally, when we represent these, we can also put them into what's called an impedance triangle. An impedance triangle places all the components of impedance like this. Our resistance would become the base of our triangle. Our reactance, whether it is capacitive reactance or inductive reactance, would be our vertical component. And our total impedance would be our hypotenuse. And by understanding the relationships between these three, we can determine what any one or all the values are going to be. So when we look at Ohm's law, we know that we taught you that Ohm's law involves current, resistance, and voltage. However, that's only true for resistive DC circuits. Now that we're talking about AC circuits and we have to concern ourselves with impedance, inductance, and capacitance, then we also have to understand that total impedance represents the total opposition to current, so therefore my Ohm's law formula is actually going to include Z instead of R. Remember, resistance is only one part of the puzzle. Now we want to have our total value, which is our total impedance, put into our Ohm's law formula instead. We have now come to the end of Module 201B. Hopefully, you'll understand how to describe the generation of an AC sine wave. You'll be able to determine what the frequency of the output of that generator is. You'll be able to calculate standard AC sine wave values, being max values, RMS values, peak-to-peak values, as well as instantaneous values. You should also be able to describe the relationship between sine waves and phasor diagrams in regards to whether things are in phase or leading or lagging. And you should also be able to describe the factors that affect total impedance. Impedance being the total opposition to current, and resistance, inductive reactance, and capacitive reactance being three components of the total impedance. Now you can return to Blackboard, do the knowledge check, and you can continue on to Module 201C.